Today we'll look at the quantum mechanics of single electron atom and single electron ions. And I want to warn you that this will entail some pretty heavy duty advanced level mathematics. But really every decent chemist or physicist should see this at least done once in their lifetime. So grit your teeth and bear it. The pain will soon be over here in an hour or so. uh, the the case I want to consider is another problem that can be solved exactly. You've already encountered several quantum mechanical problems that can be solved exactly. And those are pretty rare. Most quantum mechanical problems of any interest have to be solved numerically. They do not have exact closed form solutions. So this is one of considerable interest to chemists and physicists as well. But what I want to look at is simply one electron atom slash ion situation. So these are atomic systems that are comprised of a nucleus, uh, and in orbit about it is just a single electron. So we're looking at things like hydrogen that has a nucleus that's essentially a proton usually, um, and an electron in orbit about it. Of course, it could be deuterium and some other things as well. Uh, but for right now, we'll just think of it as a hydrogen atom. Helium ion. Helium has two electrons about it, and so we have to ionize it once. So singly ionized helium also would consist of the helium nucleus and a single electron in orbit about it. Lithium needs to be doubly ionized, and so you remove two electrons from it, and so you get a lithium plus plus ion, and so on and so forth. All of these sequence of atoms or ions here will have a single electron about it if it's ionized sufficiently so that all of the electrons are removed except for just one. And that's the model that we want to look at. Classically, the problem is fairly straightforward, and it's sort of the orbital model of an atom. So we model the atom as a nucleus, essentially a point charge, and for us, we'll have a single ion about a nucleus that has atomic number Z. So we have Z protons in it, and as a result, the nucleus has a charge of plus Ze. And in orbit about it, we have an electron that's circling about it in its orbit, essentially at constant speed. And the electron, of course, has a negative charge and has a different mass. And the simplest model will have uniform circular motion at a distance r about it. The electron, of course, is held bound to the nucleus by the electrostatic force between charges, sometimes known as Coulomb's law. So, electrostatic force law. And you may recall it looks something like this: the force between two charges, Q1 and Q2, separated by a distance r, so the distance between the centers is r. Then Coulomb's law, or the electrostatic force law, is a physical constant 1 over 4 pi epsilon naught times the charge Q1, Q2, and divided by the distance squared. Associated with any force, if it's a conservative force, you can always find a corresponding potential energy function. And for the same situation up here, where we have this force law, we also have the electrostatic potential energy function in this form. Now this is energy. Notice the difference here, particularly it's a 1 over r. The potential goes like 1 over r. But the rest of it looks very similar. The force goes like 1 over r squared. And those are always related. It's not just this force, but any conservative force. If you have a potential energy function, you can always take minus the partial derivative, really minus the gradient if it's in more than one dimension, but in this case we're only looking at radially, and the force is just this. And so those two are related. And of course, in quantum mechanics, the important thing is the kinetic energy and the potential energy. And for us, we've got a Q1 is plus ZE, and Q2 is minus E. And so we get the potential energy for this bound state, electron bound to an atom, is given by this expression here, Z E squared over R, and a fundamental constant, with a negative sign. The negative sign tells us that there's the potential anyway to having bound states to it. Well, classically, you can get the corresponding Hamiltonian. The total energy of the system really is all the Hamiltonian is. And that's just the kinetic energy plus the potential energy. And in our case, that's the kinetic energy and our potential energy we just got through getting. Here, of course, mu is the reduced mass. It really, this is so close to being the mass of the electron that oftentimes one just takes the reduced mass to be the electron mass. Even for the worst case, there's for hydrogen, the reduced mass only differs by a small fraction. I think of the real mass of the electron. But in any event, these momentums that go up here are the x, y, z components of the momentum. And momentum, remember, is mass times velocity. And so this would be the reduced mass times the velocity, reduced mass times the velocity in the y direction, the reduced mass times the velocity in the z direction, to use this, put in the expression up here, if you wanted to convert it to velocities. However, in quantum mechanics, the primary quantities are these momentum, and that's the reason we left it in momentum. Then, to obtain the quantum mechanical operator, we have to make the substitutions. The classical momentum in the x direction just goes into a quantum mechanical operator, which for the x direction is h bar over I, partial with respect to x, and likewise in each one of the subsequent directions, y and z. Position, x, y, and z, actually goes into momentum, goes into operators too. Everything in quantum mechanics, the classical quantities, go over to a corresponding quantum mechanical operator. But it turns out that for the x, y, and z position coordinates, that the operator is just multiplication by that coordinate. So if you look at that, one gets really an operator for the radius. We had the radius and the potential energy term. And that really goes into an operator. Notice for operators, I'm putting a little caret over the top, and some people use script. I always get those confused. So usually, if I'm thinking about a quantum mechanical operator, I'll put a little hat over the top. But R, remember, is x squared plus y squared plus z squared, square rooted. And so I have to make these substitutions up here, but again, these just become x, y, z. So R really goes to R. It's kind of like these go to x, the x operators. And we plug all that into the Hamiltonian here. And unfortunately, in this form, we can't use the standard trick for solving these partial differential equations that arise in quantum mechanics. But in fact, have to use not the Cartesian coordinate system. It's unseparable, essentially because of the square root. You can't separate x, y, and z dependencies because of the square root. So one can, however, separate variables in the technique we'll look at next in spherical coordinates. So this so-called Laplacian, this operator here is called the Laplacian, which is there, operator, in spherical coordinates turns into this. And so in spherical coordinates, I can write the system in this form with a single variable r here. And now we have to solve the Schrodinger equation, which is just this operator applied to the wave function in spherical coordinates. So it'll have r, theta, and phi is equal to the energy times the wave function r, theta, and phi. So now we've got the task of solving this equation here. It actually is a partial differential equation for the wave function. And that takes really some fairly advanced level mathematics. It's not difficult conceptually, and I think that's the main thing you'll need to get out of this series of lectures.